So this one will be a nice example of a mesh analysis. And so you see this, and even if it did not say use mesh analysis, it's kind of like very much set up for mesh analysis because you've got the three meshes there that you can see. And so for mesh analysis, what you want to do is for each little loop, you want to draw a circuit in that loop. It is best if you draw them all going in the same direction. If you do some clockwise and some counterclockwise, and you're really careful, you can still make it work, but it's just best to do it this way. And I'll call this one here I1, this one I2, and this one I3. And you'll notice that on any branch that is shared by two currents, like this branch right here, because our problem is to find IX. That one is shared with two meshes. Then that means that the current through that branch is really a combination of my two mesh currents. So for instance, down this middle one that has IX that we're looking for, I1 is going down this way, and I2 is coming up that way, and IX is defined as going down. And so that means when it's time for me to find IX, I would say that IX equals I1 minus I2. And anytime I write the current on the branch that is shared by two meshes, my current is going to be a combination of two other currents. So what I do in mesh analysis is I go around each mesh and I am summing up the voltage drops. So this is what I'm doing is KVL. And I'm adding up all the voltage drops, so the sum of all the voltage changes, really, voltage changes, and saying it's equal to 0. And here's how I identify the voltage changes. So I'll have my loop, so like that, and I'll follow along that loop, along my branch, and if I come to a voltage source, so say this is my voltage source right here, and I'm coming along and I'm going in this direction. When I come to my voltage source, if I go into the positive terminal, then I write that as a plus voltage. So plus voltage if going into positive terminal. And if I'm going into the negative terminal, I would call it a negative voltage. And then for every resistor I come to, it's going to be plus my current times my resistance. Because current times a resistance, that's supposed to say resistance. Anyway, the current times the resistance is voltage. But I do want to be careful if I'm on the outside branch, so like let's say this is my mesh, and this is I1, and this is I2. If I'm on my outside branch right here, that's R1, that voltage would just be I1 R1. But when I come to this inside one, and that's R2, that one, the current through that branch is I1 minus I2 times R2. So the currents that are going through the shared branches are combinations of currents. If you have a current source, then that tells you what your current is. You know what it is. And so, but what you don't know is the voltage drop across that current source. So current sources are usually not useful in mesh analysis. So if you have current sources, you're probably going to be looking for nodal analysis more than mesh analysis. Okay, so now we're going to write our mesh equations, and we'll write one equation for each loop. If we had a branch that if we had two meshes that shared, let me make sure I get this right. Where was super mesh? Super mesh. Okay, all right, there we go, current source. All right. So, oh, and that makes sense now that I'm thinking about it. All right, so if you have two meshes that the branch between them has a current source, then you treat that as a super mesh and you just write one equation for it. And I'll show an example of that after we set this one up. Okay, so I'm going to do first the left-hand branch here. So I'm going to start at this voltage source. I'm going into the negative side, so I'll write that as -2, and then plus 0.1 I1, and then plus 0.5, and then that current is I1 minus I3, and then plus 0.1 I1 minus I2 equals 0. And now I'll go along the I2 branch, and I'll start at this. I'll start right here, and I would have 0.1 I2 minus I1 plus 0.5 I2 minus I3. An advantage of making sure that all of your loops go either clockwise or counterclockwise is that this right here will always be minus. It'll always be your current minus the other one. So 0.5 I2 minus I3 plus 0.1 I2, and then I'm going into the plus side of that voltage source, so that'll be plus 3 equals 0. And then our last loop, I will start at right here at the top going into the 4-volt voltage source, so that'll be plus 4 plus 0.5 I3 minus I2 plus 0.5 I3 minus I1 plus 0.2 I3 equals 0. Now let me simplify these. So the top equation, -2 plus 0.1 I1 plus 0.5 I1 minus 0.5 I3 plus 0.1 I1 minus 0.1 I2 equals 0. And then let's see, so I have 0.1 I1, 0.5 I1, 0.1 I1. So it looks like I have 0.7 I1 and minus 0.1 I2 minus 0.5 I3, and that equals 2. My second equation, I have 0.1 I2 minus 0.1 I1 plus 0.5 I2 minus 0.5 I3 plus 0.1 I2 plus 3 equals 0. So let's see, I have minus 0.1 I1, and then I have 0.1 I2, 0.5 I2, and 0.1 I2, so that's plus 0.7 I2, and minus 0.5 I3 equals -3. So I'll just write that equation underneath this one. Minus 0.1 I1 plus 0.7 I2 minus 0.5 I3 equals -3. And then my last equation, I'm going to be really super brave and do it in one step, which means I will mess up. So minus 4 on that side. I1, I have minus 0.5 I1. I have minus 0.5 I2 right here, and that's it, minus 0.5 I2. And then for I3, I have 0.5 I3 plus 0.5 I3 plus 0.2 I3 is 1.2 I3 plus 1.2 I3. And then I don't think anyone would ever give you a 3 by 3 to do on a test, but I've got my calculator that I recommend that everyone get. If you don't already have one, it will be very handy. The TI-36X Pro. It's a nice non-graphing calculator that does all kinds of things. Including solving systems of equations. So we want a 3 by 3, and it was 0.7, negative 0.1, negative 0.5, 2. It'll be especially handy when you start dealing with a lot of complex numbers. You'll really appreciate having it because it deals with complex numbers very nicely, which you do a lot of in circuits 2. You used to do a lot of it in circuits 1, but the last few professors have not done as much of it. That doesn't look right. Let's see. Nope, it is right. Okay. So as minus I1 is minus 8.69. I2 is minus 14.9. And I3 is minus 13.2. And then if we remember, we said that Ix was I1 minus I2. So minus 8.69 plus 14.9. $6.21. amps. Let's see if that is right. 6.25, so very close. So that was it. All right. Okay, so as promised, I'll show you. I said I would show you how to do a super mesh. So let me do that real quick. So let's say that we had this. of 5 amps. Okay, so I have something where it looks like mesh analysis might be useful, and I draw my mesh loops. But you remember that I said current sources aren't particularly useful in mesh analysis. Well, they are if they are being shared by two meshes, and that that you can have a resistor in there as well. That doesn't affect anything, but then that makes this useful. And what it does is it allows me to treat this as a super mesh. And here's how you do it. I would call this first one I1, and this I2 and this I3 just as before. But my first equation is going to be that I2 minus I3 equals 5. Because remember that current down that middle branch is I2 minus I3, and it has a current source. So that has to be the value of that current. And then when I write my mesh equation, I write one equation for both of these meshes together. And I just go around the outside. So this would be 2I2. So I get this one. And then I go around. And then I come to this one. And that would be plus 4I3 equals 0, because that gets this whole loop. And then my last equation, I go to my other loop. I'm coming into the minus side of this 3-volt voltage source, so that's minus 3 plus I1 equals 0, plus 1 I1. So I have... Yes, yeah. It doesn't affect finding these. The only thing I would need it for is if the question said find the voltage across the 2 ohm resistor, in which case I wouldn't need to solve the problem because I already know the current across it. So I'd be done. And not only that, I have a silly circuit here because look at this right here. That's that bottom one. And so I think I might have, well, I don't know. It's okay. So I know that I1 is 3. So I've got that. And then I have these two equations that I would solve that both have I2 and I3 in them. And I could solve it if I wanted to, but I just made this problem up to show you what it was like. Okay.